All right, let's build a super fast study guide to help you absolutely crush alkanes in your chemistry course. You ready? Let's jump right in.
So, alkanes. They kind of get a bad rap, don't they? You've probably heard them called boring, stable, or just plain unreactive. But is that really the whole story? Are they truly the most uninteresting topic in all of chemistry?
I think we can prove that wrong. In fact, over the next 5 minutes, we're going to build the only study guide you'll ever need for alkanes. We'll cover what they are, how to make them, and yes, how they actually react. So let's get to it.
First things first, we have to build a solid foundation. So what exactly is an alkane? Seriously, getting this right is the absolute launchpad for basically all of organic chemistry.
Okay, here it is. The core definition you've got to know. An alkane is a saturated hydrocarbon. Hydrocarbon, easy enough, made of only hydrogen and carbon. Saturated, this is the key. It means it's packed to the brim with hydrogen atoms connected only by single bonds. And that general formula, CnH2n plus 2, oh yeah, you're going to want to burn that into your memory. It's the simple rule. For any number of carbons, an alkane is holding the maximum number of hydrogens it possibly can.
Now what's so cool is how all these properties just click together. Because they're saturated with those strong single bonds, alkanes are super stable, which makes them pretty unreactive. And since carbon and hydrogen have a very similar pull on electrons, the molecules are nonpolar. Now here's the so what. With no real positive or negative hotspots, they're basically invisible to attacking molecules like electrophiles or nucleophiles. They just don't offer anything to grab onto.
Okay, time for our first big checklist. If you need to actually make an alkane or understand where they come from, this is the essential knowledge you've got to have in your back pocket.
We're going to cover 4 key pathways. My advice? Treat this next slide like a flashcard. The starting material, the name of the process, and especially the reagents and conditions. Those are classic exam questions. So let's lock them in.
And here they are, the big 4. On an industrial scale, we get alkanes from crude oil using fractional distillation. Simple. But in the lab, you have options. First, you can start with an alkene and hydrogenate it. That's just adding hydrogen gas with a nickel or platinum catalyst and some heat. Second, you can reduce a halogenoalkane using a powerful reagent called LiAlH4 in dry ether. And third, you can take a carboxylic acid salt and decarboxylate it using soda lime, which is just a mix of sodium hydroxide and calcium oxide and heating it up really strongly.
All right, so they're stable, but they're not invincible. Let's move on to our second checklist. Let's see how we can actually force these supposedly unreactive molecules to do something interesting. You really only need to know 2 main types of reactions here: combustion and substitution. Combustion is just a fancy word for burning. If you have plenty of oxygen, you get complete combustion, which makes harmless carbon dioxide and water. But, and this is a big but, if you limit the oxygen, you get incomplete combustion, which produces deadly carbon monoxide. The other major reaction is free radical substitution. This is what happens when you mix an alkane with a halogen, like chlorine, but, and this is crucial, only in the presence of sunlight or some other source of UV light.
And listen up, because this is a big one. If there is one single reaction mechanism you absolutely must know for alkanes, it's this one: free radical substitution. It's a classic chain reaction, and it all goes down in 3 distinct stages.
So let's break this down. First up, initiation. The UV light acts like a starter pistol. It zaps a chlorine molecule and splits it perfectly in half. We call that homolytic fission, creating 2 superreactive chlorine free radicals. Next, propagation. This is where the chain reaction kicks off. A chlorine radical slams into an alkane, rips a hydrogen off, and creates an alkyl radical. This new radical then attacks another chlorine molecule, forming our product and a brand new chlorine radical, which then goes and starts the whole process over again. It just keeps going until, finally, termination. This is exactly what it sounds like. The party's over when any 2 free radicals bump into each other and combine, forming a nice stable molecule and stopping the chain reaction cold.
Whew, we covered a lot there, and fast. So let's pull it all together into one final, ultimate study card. Seriously, this is the one you want to screenshot for your final revision. So here it is, the whole story on one slide. Their identity? They're saturated, nonpolar, follow that CnH2n plus 2 formula, and are generally unreactive. How do you form them? Lock in those reagents: hydrogen and a nickel catalyst, LiAlH4, and soda lime. How do they react? Remember the conditions: excess oxygen for complete combustion and a halogen plus UV light for substitution. And that all-important mechanism? free radical substitution, with its 3 steps: initiation, propagation, termination.
And just like that, you've got it. You now have a solid grip on the fundamentals of alkanes. See? They're not just some unreactive topic. They are the essential foundation, the bedrock, on which all the beautiful complexity of organic chemistry is built. So the only question left is, now that you've mastered the foundation, what are you going to build with it?